Hey everyone, Adam the Tutor here, coming at you with part C of our mass spring system problem. So, the problem basically asks us approximately what time, and we've labeled it as, didn't mean to move that. So again, it's asking us what time t sub d does the amplitude decay to half of its value. Now, the way that I asked this, I was kind of looking at it in between videos. This isn't actually what I meant to ask, because that would actually be extremely difficult to determine. What I meant to ask was at what time TD, let me go ahead and write it down. So at what, no, that's a funny looking W. At what time T sub D does the maximum amplitude decay to half. Should be an L right there, and don't need anything right there. To half, and actually let me move this down a little bit more, just a scooch. There we go. To half of its original value. To half of its, and there should be a apostrophe there, original value, which, as we can see in the equation above, if I just come up here, right, at t is equal to 0, this guy is 0, this guy is 1, this guy is 1, so it's just x naught, right? Which makes sense, right? Because this is our position function, so at time t equals 0, it should be in its initial position, right? Original value, x naught. And this should really be capital. Split hairs over that, though. Okay, so this is really what I meant, because finding the times when this is equal to half, it would be very complicated to do that, and that's not really it's not even really of interest. Physically, what is of interest is this, right? Basically, we're asking, hey, what time, does this system lose enough energy to where it can't even reach half of its initial displacement from its starting or from its equilibrium position? That's really more. It's a lot more interesting question. So now, how do we do that, right? Well, basically, what we're going to do is we're going to utilize the fact that, hey, it's an oscillating system, right? So for now, we're going to ignore this this exponential that's off to the side of the complementary solution. So first, we're just going to focus on the sines and the cosines. Well, we know that the period of such an oscillation is going to be 2 pi over big gamma, right? So basically, that is when, if we didn't have this, this dampening thing going on, let me get a nice long t-axis there. T and x of t, and we'll call this no damp, right? So no dampening, right? We'd start at x naught, and it goes something like this, right? So this would be x naught, this would be x naught. Let me just do a couple more. It's not going to be the greatest, right? And this is x naught. So this is all x naught, and this should be on here. So we'll just pretend that it is. And this is minus x naught, so minus x naught, right? Okay. And that's basically what would happen. Okay, so this is t is equal to 0. This is pi over 2. Actually, I'm sorry, this is pi. This is 2 pi. Well, actually, pi over gamma. 2 pi over gamma. And this would be 3 pi over gamma. And this would be 4 pi over gamma. Right? And you kind of get the idea, right? This is when our function is going to be maximum, right? So, basically, now what we really care about is we want to find the n value, right? Because these are integer multiples of pi over gamma, right? So really, actually, this should be n where n is a member of the positive integers. Right, z positive. I mean, it could be negative too, but for physical purposes, or not even really physical purposes, but just for niceness. So n is a positive integer, including 0. So including 0. This is kind of my notation, I guess. So basically, now what we need to find is basically where, lost my thought. What we need to do is we need to determine which of these points, basically which of these times, does the maximum amplitude fall to half of its value. So basically what that would entail is now we have to come over here to xc of t, right? Or x sub ct. And basically we're going to plug in, right? So here we go. So xc of t is going to be equal, or well, actually I didn't want to do of t, I wanted to do of our period that we have established. So that would be 2 pi n over gamma is equal to e to the minus gamma over 2 pi n over gamma. By the way, this is our time t sub d. And then times, well, let me come back because I forgot my constants that were up here. So 1 over gamma times the quantity v naught plus gamma over 2x naught. Okay. Well, actually, that's not even really going to matter because our time t is 2 pi n over big gamma, right? So sine of gamma times 2 pi n over gamma is just 0, right? So then we have x naught, and then cosine of gamma times 2 pi n over gamma would be -1 to the n, right? Because if we plug in for, or I'm sorry, not 2 pi. Why do I keep doing 2 pi? This should be just pi. Pi n over gamma. So, right, okay. Right, the period is 2 pi n over gamma, but this right here, if we start here and we come to here, that's a half a period. That's not a full period, right? So then, and of course the same argument holds because basically the sign would be pi times n. It'd be sine of pi times n, which would be 0. So this will be -1 to the n, and then, okay, so we already have our exponential. Okay, so we're good. We're good to go now. Okay. So, basically now, this -1 to the n is essentially not well, here, let me just, let's do it, and then I'll justify why I'm going to do after I do it. So, at this time, t sub d, we are basically going to have that this is equal to 1/2 x naught, right? Half the amplitude, right? So, essentially, our x naught's going to cancel out, and we're going to be left with e to the negative gamma pi n over 2 big gamma, right? Times negative 1 to the n, which is equal to 1/2. Okay, now here comes the part where I am going to discard this negative 1 to the n. Now you might be asking, okay, why can't I just do that? Well, basically because I'm going to take the natural log of both sides. And in order to find the n that I need a real answer for that. And it's not very physical because we care about basically the distance, right? We're not really caring about the exact displacement. We're caring about the distance of the spring from the equilibrium position, which is, this is the equilibrium position. Equilibrium position, right? This t-axis, right? This t-axis is the equilibrium position. And this negative 1, positive 1 doesn't really matter for that. So we're just gonna ignore that, and we're going to instead solve e to the minus gamma pi n over 2 gamma is equal to 1/2. Well, you take the natural log of both sides, and you get negative pi n over 2 gamma is equal to the natural log of 1/2. And then if you want to solve for n, you get that n is equal to negative 2 big gamma over little gamma pi natural log of 1/2, right? So this is the n value, and basically you'd have to round this to an integer, because I can already tell you this is not going to be an integer. So you'd have to round this to an integer in order to find the time td that it becomes 1/2 of the amplitude, right? So, and remember, we wanted to know the time d. So this is it. This is good. So this is our n value, right? So our time t sub d is going to be equal to pi over gamma times minus 2 gamma over little gamma pi natural log of 1/2. And so then, let me move down. So then our time t sub d, well, this cancels with this, and we get negative 2 over little gamma natural log of 1/2. Which this is positive, right? Because if I have a natural log of a fraction, that's going to be negative. Negative cancels negative, and I get that this is positive. So this is our answer, right? Depending on gamma, right? This is our answer. So that does it for this video. And in the next one, we're going to look at part D, which is going to require us to be a little bit more clever, and we're going to have to solve this differential equation again. But it won't be too bad, I promise. So, thanks for watching, and I will see you in the next video.